Hello, this is just a quick video answering a question which has come up a few times in class, and I know I'm going to be asked it again in the revision session, so I thought I'd do a video on it. People might find it useful, so you can refer back to it. And I'm going to show you the three different ways. There is another way as well, which I won't show you because it takes too long. But there's lots of ways you can handle these questions, and they are weird as well and difficult. There's no doubt about it. But they're not. They don't take that long to do. But it's just hard sometimes getting your head around it. So it's one of these ones where you've got some kind of collision. So it's going along at 2, 3i. It does help if you draw these roughly in the right orientation, and then it rebounds 3 minus 1. So roughly around there, 3 across 1 down. And we don't know, though, what the situation is with the wall. It's not necessarily parallel to the vector I. So let's put it a little bit wonky like that. In fact, I'm going to make it a little bit more exaggerated just because I know I'm going to draw lots on this diagram. So, we're going across at 3, 2, is it? Or something like 2, 3. Oh, so it's steeper on the Y. Yeah, that makes more sense. Boing. In fact, let me make it a bit clearer. Up like this. It's just looking even more wonky now. Let me just try and get that right. And then bouncing off at 3 minus 1. Yeah. So that's the situation we've got. And we don't really know the orientation of the wall. That's the problem. Now, there's lots of ways you can handle this, and the question actually tells you how to handle it in many ways, because it says find the impulse first, and that's because the direction of the impulse is what's going to tell us how we can find E. Now, that's easy to do, because I is simply m times v minus u, which works perfectly in vector world, so we just do 2 times 3 minus 1 minus 2, 3, and that's going to give you 2 minus 8, yeah? And so let's draw that on a diagram in a different colour. It's going 2 across, 8 down. So that's the all-important impulse. Okay, right. Now, the way this is always presented, part B, in the solution bank or anything like that, they do this in a wonderfully quick method, and it is there's no doubt about it, it's a great method. You can't help but think, yeah, once you get it, it's really clever. What I do is this, essentially. This is my way of understanding it. It's not mentioned in the textbook as well, it really isn't, so it's definitely something you want to be aware of, because then you see the mark schemes and you're like, oh, they're doing this some kind of clever trick. Well, here's what it is. Basically, if this is vector u, yeah, which is 2, 3, fair enough, I'll put 2, 3 on the other side, but this would work with any vector, and you want to find the component of the speed acting perpendicular to the wall, which is exactly what you need for coefficient of restitution, because remember, coefficient of restitution isn't affected in that direction, parallel to the wall. It's only affected in perpendicular to the wall. In other words, it doesn't slow down parallel to the wall, it only slows down on the bounce, perpendicular bounce off of the wall. Now, bearing that in mind, what we really need to find here, therefore, if we call this angle, let's call this angle up here alpha, yeah, we really need to find u cos alpha, yeah, and also equally over here, it would be really nice to find if this is v, and v is obviously 3 minus 1. We really need to find v cos, let's call it beta or whatever, yeah, beta. We really need to find the size of v cos beta, because that would be the speed perpendicular to wall coming off of it. In other words, we want to compare these two coefficients, and E is just simply going to equal, now I always get this the wrong way around, it's rebound over approach. In other words, it's going to be equal to v cos beta over u cos alpha. Yeah, this is essentially the trick I'm going to use. Now, I don't even know why I'm writing all this down, because normally I don't bother, because you don't really need to, because the trick you need is to do with the vector I and u. Now, if that's alpha, z angles here, which means if I drew like the impulse but negative, like this is minus I, then this angle here would also be, if I extend the line, extend this line here, that would also be alpha. So in other words, what I can now see is if I do the following, here's a clever trick. Basically, if you do u cos alpha, well, that's actually going to be the same as u, sorry, not in a modulus, but u, the vector u, dotted with the vector I hat, yeah? And that's because if we move this over here, this would just be the size of u, and the size of I hat, if I mean unit vector, that's what I mean by when I put a hat above a vector, unit vector, that would just give me the angle between it, if you see what I mean. That is just the standard formula for the angle between two vectors, and I could rearrange that really quite cleverly because that equals 1. I can ignore that, just move that over here, and I get this result. U cos alpha, in other words, the perpendicular speed, is equal to just u dot I hat. Yeah, and actually, sorry, I need this to be minus I hat as well done. I can put a little minus in there. Yeah, and I'm definitely using this angle. And so all I need to do is just do 2, 3 dotted with 2 minus 8. Yeah, and that's what you'll see them do in the mark schemes. Yeah. But it's supposed to be a unit vector, so let me just put on the end 1 over root 68 because that's the length of that vector. Yeah, that's what u cos alpha actually equals. Yeah. Now you can actually end up ignoring 1 over root 68 because it also pops up on the same side on the other side. It's just a scaling thing. Both of them are going to have a 1 over root 68 on the end, so it'll cancel in the division over here. So let's have a look at this. V cos beta. Well, what we're going to do, we're just going to take the final velocity 3 minus 1 and dot it with 2 minus 8. Put a little 1 over root 68 on the end because that's definitely giving me this speed here. And I suppose I better finish the calculations. What do I get here? Now, did I remember to change the sign on the impulse on this first one? I put a minus I there. No, I didn't. So let's just put that one and move that minus up to here. Yeah. It's important that you do that. That's the one thing which can go wrong. This beta is the same as this beta here. Do you see what I mean? So it is the angle between the impulse vector and the vector v, and so you're going to get just the value you need here. We're going to get 6 plus 8, which is 14 over root 68, whereas this is going to be minus 4 plus 24, which is 20 over root 68, and therefore E is just that one divided by that one, and that comes to 7/10. Yeah, but that's the trick they're using. It's this trick right on the wall. Make a note of it. It comes in really, really, really handy if you like their trick, and they do make it look really quick. Okay, just for my own entertainment, you can probably stop watching the video now if you're happy with that, because I'm not going to bother with part C. But here's method 2 and here's method 3. Now method 2 is what Ksenia, if you're watching, this is what you tried to do. I just want to show you the method does work. Yeah, method 2 is to use matrices and rotate. Yeah, it's not as slick as the method we just used, but use matrices and rotate. And then method 3, I'm going to show you crazy complex numbers approach. Okay, so method 2. Yeah, it doesn't hurt to learn new methods anyway, it really doesn't. So matrices, yeah. Now, how far have we got to rotate this thing so it's completely flat? Well, if we call that alpha there, that will, oh no, let's not call it alpha like we had alpha before. Let's just think about this. Can you all see? I hope anybody watching at home can see that if I was to draw, oh, let's use a different colour. Okay, blue. If I was to draw a line down here, and I'm sorry this is so unstraight, that this angle here, let's call it theta, is the same as this angle over here, theta. Think about your mechanics work, like, you know what I mean, like, you know, inclined planes. That theta is the same as that theta. So I need to rotate this theta degrees. Now, Ksenia, if you are watching, you drew your anti-clockwise arrow as a clockwise arrow, and I think that might have been a mistake you made. We've got to rotate this clockwise, yeah, by theta degrees. Now, what is that? Well, we already know this vector is actually, you know, we can use the fact that this vector is, what was it, 2 minus 8, I think? I've actually lost the working. Yeah, it's 2 across to the right and 8 down, isn't it? So I can easily find that vector. It's just tan theta equals a quarter, and you found this successfully. That instantly gives you sine theta is 1 over root 17, and cos theta is 4 over root 17. Cool. Now, we want to rotate it, therefore, you know, theta degrees clockwise. Yeah, that's the direction the clocks go, and so we want to rotate this whole plane down, and then we can just compare basically the y components, and the x components should be the same. Now, how do you rotate something clockwise? Well, in the formula book they do actually give you the formula for this, so we might as well use it, but they give it for anti-clockwise. But it's very easy to go from anti-clockwise to clockwise. All that's going to happen is the minus switches from that sign to that sign. Yeah, so if you want to go clockwise, then what we're going to do is cos theta, 4 over root 17, minus sine theta, that switches to there when you're going clockwise. And so we're going to have minus 1 over root 17, then we're going to have 1 over root 17, and we're going to have 4 over root 17 again. And I'm going to times that by my u and my v, yeah, because this is u and this is v, and I want to rotate these basically round, and then I can just investigate the y components and find a coefficient of friction, of restitution, sorry, that way. Okay, so 2, 3, you get 8 root 17, 11 over root 17. And then for the other one, minus 2 over root 17 plus 12 is 10 over root 17. Okay, cool. Now do the same for the other one. It's a bit cumbersome, but it works. Okay, we're doing it with 3 minus 1. We're going to get 12 minus 1, 11 over root 17. That tells me I've done it right. They're supposed to be the same, because remember the speeds in the x direction, once you've rotated it in the x direction, should remain exactly the same. Whereas this one changes to minus 3 over root 17 minus 4 is minus 7 over root 17. Right, you always expect this sign to be the opposite of this one, and you can just say after you've changed the sign on this one that e is 7/10, because essentially, it's going, it's 70% of that one, if you see what I mean, after it's bounced off the wall. Because what we've found is we've flattened it out now and realised that afterwards that distance is like 11 over root 17. Yeah, and sorry, this one's 11 over root 17 parallel to the wall, but and that one's 10 over root 17, and this one's obviously in the other direction, minus 7 over root 17, because it's a vector component, and this is 11 over root 17. See what I mean? The speeds in that direction are the same, but these two, you can just compare the 7 and the 10, say is 7/10. So that's another method of doing it, and that's the way that you were trying to do it, and that's, yeah, the way it does work, if you see what I mean. Okay, the last way of doing things. I just like this method. It's a crazy method. I'm going to draw it all out again. Okay, this is complex numbers, yeah? And it's not as bad as you think. And works a bit different, I think, to the others. I think it just ever so slightly works different. So we had this, we had this, we had this, and we had an impulse. I think this could be used really effectively. Okay, right. What do we really want to do here? Well, when you multiply by a complex number, you just basically rotate it. So if you, just to give you a quick recap on complex numbers. Let's take a really simple one. Like, if you take the number 1 and times it by I, what does it do to it? It rotates it 90 degrees, yeah? And if you look at the complex number z equals I, if you wanted to represent it in modulus argument form, it would be, 1e to the I pi over 2. Yeah? In other words, like, what happens when we times a complex number by, any number by a complex number? We just rotate it that far. Like, if you imagine this as a vector, what's happened to the complex number 1 plus 0i here after you've times it by I? You've ended up at I, yeah? Now, look at your number I and actually ask, well, what is it in modulus argument form? It's 1e to the I pi over 2, and that's, that's clearly, you've just rotated your number by pi over 2, because that's 90 degrees. Yeah, that's what complex numbers do. You can, every time, what are you doing when you multiply two complex numbers together? You're multiplying the moduli. Don't worry about that. But you add the arguments. Yeah, you add the arguments. In other words, you turn it, you rotate it by that by that amount. Okay, so how am I going to use that? Well, what I'm going to do is I'm just going to think, wouldn't it be nice once again to flatten this down here? Yeah. Now, how can I get a complex number which turns it that far? Well, just like before, I realised that was 8 and that was 2, yeah? Well, that means that, if you're looking at this would be like 2, 8 across, 2 up, if you see what I mean. What I'd like to do is therefore think about a complex number which is 8 across, 2 down, yeah? Because if I multiply by the complex number 8 minus 2i, then I'm just going to rotate it that far, because it's got a negative argument, which is what I want. I want to turn it in that direction by that amount. Yeah. Now all I've got to do is just take my my initial speeds, but represented in complex number form. So 2 plus 3i for my 2, 3, and times it by 8 minus 2i. Yeah. Now once I've times that out, what do I get? 2 plus 3i times 8 minus 2i. I think it comes to 22 plus 20i. Yeah. And now I'm going to do the same with the other one, which was 3 minus I. And I'm going to multiply it by 8 minus 2i to rotate it, and I get 22 minus 14i. And this time it's going to be the imaginary components, which I'm just going to look at, because these two, notice they're the same. That's telling me I'm doing it right. And I can just say basically this is like, e is just going to be that one divided by that one after I've made that positive. Yeah, it's going to be 7/10. Okay, that's a really crazy way of doing it. Think about what I'm doing there. It's like it's something really like sly, devious. I just wanted to flatten it out, so I'm going to, how do I flatten out something which is at that inclination? 8 across 2 up, a gradient of a quarter essentially. Yeah, I'll just go in the other direction and do 8 minus 2i. So I have to change the sign on that, and then yeah, it works out beautifully. Okay, hope you enjoyed the video. Use whichever method you like. I don't care. Just get it right. Probably the quickest one is method 1, and it is slick, and you'll see it in all the mark schemes in Solution Bank. So